is going on? I think, yes. All righty, so today is the 17th, last day of new information. Hooray. And we're gonna mostly do integration by parts. That's the main topic for today. These are pretty cool. And then I'm also going to mention just a little bit of the integration tables that are at the back of the book, because integration is different than derivatives. Like, there are a lot of weird cases. So integration tables and how we could use them. But we also, like I've been saying to Trey too, also use technology. If you have some kind of app or a calculator or whatever that could do complicated integrations, start practicing with that too, because I mean they get to a point where they're just out of hand to do them by hand, and people use
do you have like an example of like what kind of tech has that? So are you talking about like a TI 82-3 or Desmos or?
Yeah, I don't know how to integrate in Desmos, but I do know how to find the derivative now. So I do know how to do that, but I haven't learned how to do integration yet. But yeah, I'd use a TI-84, or they have them online for free too now, or like an app for your phone or something like that. Like, there's other math software like Maple. I don't know if you've used Maple or MathLab, Wolfram.
MathLab I heard of, and the other one, yeah, but I didn't hear.
Yeah,
I never heard of the first one, Maple.
Maple, yeah. Software is great, and as a student, you might be able, if you keep on with math, for example, like none of the stuff we're doing needs technology to solve them, but it just is nice for backup. You'll see what I mean. Sometimes that it's like, oh my Lord, this is just hairy. Might as well use technology when you can, you know? But the TI-84 for sure, you can, it has an integral command even, and then it just, you have to do definite integrals. It needs the endpoints to calculate it. Actually, the higher end, the more recent TIs, I have an 84, so that's why I know the best. But the more newer ones can do it in indefinite form too. I've seen that. So if you ever get like a bookstore scholarship or something where you could get a nice graphing calculator or math software, you can. So software, what I just mentioned was Maple is one that our book talks about. And one of my students he came from Mines, actually. He used Maple a lot. He really liked it. And then there's also Wolfram. I think Wolfram Alpha is the phone app, and it's kind of limited, or Wolfram MathLab. Is it MathLab or MATLab? I think it's MathLab. And then there's some other ones too that are kind of old, but you could look around if you go into this and you're interested, you know. Otherwise, don't worry about it. There's probably newer ones that I don't know, because I try to stay away from the technology a little bit so that I don't lean on it too hard. So I want the students to be able to do this without it. So anyway, so we're going to do that, and then Desmos, I was going to show how to use that to find the derivative. That's pretty cool. That's it. And then the final exam review topics. I think I'm just gonna, I don't know. I've already given 9 assignments. I don't know if I'll give another assignment today. Maybe today's will be optional assignment, just some review problems to get ready for the final. But you could just look them over too if you're once you're all caught up. You'll probably be fine. The final will be a lot less material than the midterm was. So usually people do better on the final than they did on the midterm. So hang in there and you shall probably do well. But anyway, so today let's start with integration by parts. And what you missed this week, the main things that you missed, I'm thinking right now while I'm writing, is finding the arc length of a curve. That's a fun one. We'll practice just one before we go of that one. And L'Hopital's rule for limits, finding limits. So we jumped back into that. But let's not get, I'm not going to put the cart before the horse. So integration by parts is based on the fact that the product rule. It's based on the product rule. Which is if you have f of x times g of x, then the derivative is the derivative of the first times the second plus the first times the derivative of the second. That's our old product rule from long ago. And so they rearrange and mess around with it a little bit. Here, I'll explain. So the derivative, here, let me write it this way, a little bit neater. Derivative of f of x times g of x equals derivative of the first times the second plus the first times the derivative of the second. And they move the things around until they can, let's see. So if that's the case, the derivative of this equals that, then the antiderivative of this whole thing, or the integral of this whole deal, is going to equal that, because they're inverses, remember? So the derivative, if you take the antiderivative of the derivative, you end up back with your original. So that's what it's based on. You don't have to prove this or anything like that, but it's where it comes from. And then they rearrange some of the values and end up with the integral of f of x times the derivative of g of x equals f of x. And this isn't the way that we use the formula because it's harder looking like this. G of x times f in derivative of x. There. So what the heck is this supposed to mean? But anyway, that's where it comes from. Again, it comes from just a rearrangement of the product rule. And we use it because there are times when we get something that you can't just find the integral. Use this formula, though, is what we do. The integral of u dv equals uv minus v du. So this is the same thing. This is an easier term, easier on the eye. Here's u. There's two different functions that we're talking about together, kind of like in the chain rule. That's the dv. And then this is u times v. And then the integral of v times du. And so this is how much easier to look at, but it's the formula that we use. I just wanted to briefly explain where it came from. So we can practice one. Right out the gate. Where's my first example? So here's an example. If we had to find the indefinite integral of x sine x dx, we can't do it. We can't just separate them because it's multiplying. If they were adding, we could separate the terms, but not when they're multiplying. We can't use u substitution to cover that whole thing. It would just be a mess. So we can't use the u substitution that we did in chapter 4. So what we do is decide what's u going to be and what's v going to be for our formula. So you can pick either one, but you usually pick the one that's going to, for you pick the one that's going to have its derivative be simpler than the original. So I'm picking x because the derivative of sine is just going to go over to cosine, remember? So that's not going to change up very much. But if we so we go make a little box like the other time when we were doing the little box. Let u equal that x, and then the derivative of that is what du is. And then v, we don't know what that equals yet, but dv, we could name that as this piece. And then we have to figure out, well, and this is the great thing about integration by parts, that we don't have time to get into the really complicated ones, I'm sorry to say, but the great thing is we're doing integration and derivatives both at once. It really twists our brains up. So we have to figure out what's v going to be so that the derivative of v equals sine. So we're really finding the antiderivative of sine, and we're going to put it up here. So it's negative cosine of x. Okay, then we double check, make sure the derivative of negative cosine goes to positive sine. Derivative of x goes to 1. And then we're ready to use the formula. And it's the setup that's half the battle, honestly. So I'll write it right up here above the formula, so we don't have to look at the messy version of the formula. Okay, so the integral of x sine x dx is going to equal u times v Hi, Trey. How long have you been here? That's great.
Sorry, that was supposed to be private.
Oh,
I've been here for 15, 10 minutes. 10.
Oh,
Hey,
good.
he came into class like 5 minutes after, so
Yeah, I think it was like
he's
5
been here.
minutes after it
Yeah.
started.
Oh, good.
I was just watching.
Sorry, I didn't notice and greet you.
Oh, no worries, no worries.
So here's the UV right there, minus, and you already got it there, so that's sweet. Minus the integral of v, which is negative cosine x, times du. I'll just put the 1 so we don't forget that we do times it by whatever the du was. And then we always put dx on the back of an integral. And then simplify that down like you did. So it's going to be negative x cos x plus the integral of cosine is sine times 1 dx, and that's all covered, plus c for that constant. So there we go. Really got a frog in my throat today. Sorry about that. Does anybody do did either of you have a question or anything from there?
I like you set those up though. I'm gonna start doing it like that. In that little table on the bottom.
Yeah, I like it too.
That's why I got the answer so quickly, honestly, it's because you're set up. So I'm gonna start doing that.
Fantastic. All right. Okay, let's do another one. I'll just leave this table here and get these off. Erase this. And we'll do example 2. Shoodly-doo. Okay, example 2 is ln x dx. In this one, I was like, well, there's only one thing, but we don't have a formula. I mean, well, there is a formula in the back of the book for the integral of natural log. But we're going to do it this way. So you let u be ln x. So du is 1 over x. So we learned that earlier in the week. And then let dv be just 1 dx. I should be putting a dx on the back of each of these integrals. My bad. And then we do the antiderivative of that to find what v equals. So that's going to be x. So it seems for a second with this one, I like this example. It's a book example. I like it though because it has natural log and it looks like we made it just harder than it was. But this one sweet comes out real sweet. So u times v minus the integral of v du times du. So I'll see if anybody beats me to it. Here's u times v in the right order that we usually write them. Minus the integral of v times du. If you're ever doing these tired, it's easy to forget and put them in the wrong place. And then we can simplify that x times 1 over x. So I'm going to just erase that and put the x times 1 over x equals just 1. Good job. I'm fire today.
Fired
You
up
sure?
for the final.
You are, I see. Fired up. Super.
It's Friday.
It is. Okay, now before I do the third example, because that's a 2-stage one, the third example from the book, I'm gonna do number 3 from the textbook. Well, we are together. So we're gonna find x cosine 5x dx, the indefinite integral of that. So remember, here's our formula. And again, when people are, sometimes we pick the wrong u. We should be able to do it either way. If you could pick u to be cosine 5x also, but it's not going to simplify down that, like the integral of cosine goes back to sine and cosine and sine. It's just, it never cleans up. But the derivative of x is going to be just 1. So that's how I usually pick the right u and v the first time. But even after all this time, I sometimes don't pick the right one. I'll be like, oh my gosh, I just made it so hard. Not this one. I already did this one in advance.
So you can pull out the 5, then that counts as a constant, or does that not how that works?
Oh, you have to put that whole thing in here. Well, you'll pull it out in a second though.
Okay,
Cosine 5 goes there.
but in the beginning, oh, you can't factor it out right away.
Oh,
Okay,
nope, because
got it.
it's locked in there. Yeah. If it was here, you could. Good question. Mhm.
Yeah. Okay, I just wanted to make sure.
Yep. And then v right here is, it's really, if you ever get mixed up, it's the antiderivative of cosine 5x, which means the integral of cosine 5x, which would be sine 5x times a fifth to balance out that chain rule would have us. Well, hold on, I'll just write it this way. See what I mean? We're thinking back and forth. There. If we look at this one, this v, the derivative of that would be 1/5 times cosine 5x times 5. And the 1/5 and the 5 would cancel out. We'd end up with this. So that's what we want to make sure. We can always double check. Is the derivative going to equal this? Is the integral going to equal this? When they're a little weird like that. So that's the setup. Let me pause it a minute, see if anybody wants to go ahead and do that before I go further. And then dv is the other guy that's sitting there. And then remember the derivative of e to the t is the same as itself. So the integral is also the same as itself. And then we could go, okay, it's going to be t squared e to the t minus e to the t times du, which is this. So if you don't want to forget that duh. Don't forget the duh. Because that's going to mess it up. That's not a final answer now. We're not done yet. So we have to, we might think, darn it, maybe it's never going to work. It go around and around in circles, but it will. Here's our second box that we'll use. Look at a different color. Now I'm going to make u equal 2t and du is 2. That'll solve that problem actually. The dv same as before. And what I do on the chalkboard, well, it's a whiteboard now. On the whiteboard at school, we'll put it up on a whole double whiteboard, and it's all like neatly, you could see it all. But I don't recopy this yet. I'll just bring it down here to the final answer. And the minus sign is going to go there outside of a bracket. And then just put a bracket here. Okay, so now the new uv is down here. 2t e to the t minus the integral of e to the t du.
Oh, you got it.
So that's gonna be just this. This 2 could come out in front here. And the integral of e to the t is itself. Then I just throw that down there. And then again, like I was saying in remember when we were doing some of those integrals and derivatives, and you could you factor to the end to make it look all neat and tidy and stuff. That's what I was trying to see if we're supposed to be doing that in these, but we're not. You don't have to. You just write it like this. Let's carry that negative sign through plus c. Some constant. Because see, like 2, no, e to the t could factor out all of them. And that's why I was like, should I keep going and factor out e to the t? But no need. That's the official answer. So we could do definite integrals this way too. Once we have values, that's more fun. We could substitute them in and find a area under a curve or a distance or whatever. You guys have any questions about that one?
No, I like these.
That's great.
You can work out a little bit. Nice and clean.
They are clean. They do feel that way. Okay, here's one of my other faves. This is the book exercise 11. So we're not doing anything other than this today. Well, I mean, I was going to review the arc lengths and the L'Hopital's rule for angel later. But you already saw that yesterday, Trey, so.
Oh yeah.
I just always rewrite the formula if it's new. Usually, like I said, it would be up on the board the whole time or on a poster in the room. But so exercise 11 is this: t to the 4th ln t dt. So this is the one. This is the one that I picked the wrong u at first. At first I thought u would be t to the 4th because it seemed like that's the way that it would make life more simple. But then I saw that the derivative of ln t, well, we just did that actually in the examples. So we did do the derivative of ln x, but it's a little bit, no, we did that. We didn't do the derivative of it. We did the integral of ln. Yeah, but it's a complicated one, a little bit complicated. So anyway, so u is not the t part, it's the ln in this case. So if you ever pick the wrong u, no worries. You can just go back and fix your little info box. And then dv is over here. That's the other term or the other piece. And then v is, that's no big deal. Remember, that's just the antiderivative of t to the 4th. So add 1 to the power and divide by that number. So it's a fraction, but it'll be really nicely workable. This one, I'll pause it again and actually go ahead and work on that one. And I'm going back through because I think I turned off the recording during this one. So that was that one. This one, the recording, I think, was back on here. No.
When is our final, Jane?
It's Monday.
Monday, okay.
Monday during class time. If anyone wants to take it early, they can.
Sweet.
It won't be as extensive as the midterm. Probably about half that long. I don't
Cool.
think it's. I don't think the material's as hard either.
I was just gonna say. Seems like the material's a bit less intense. Less rigorous.
So we're gonna have U times V. I write this term first because it just, to me, it looks cleaner. So
Oh, yeah.
there's U times V minus the integral of V. Oh, let's just put 1/5 here, so we just have T to the 5th to deal with, times du. And then these cancel one off, which is nice. So we're going to find the integral of T to the 4th instead. So T to the 5th over 5 times ln T minus 1/5 times T to the 5th over 5 plus C. And then I could just clean up that. I'll clean up that second term a little bit. These are very abstract when we're talking about indefinite integrals. And sometimes people forget, like, what did I even find? And that's why we do so much of that stressing the area under the curve and stuff like that in the beginning. And now we'll do one that has some values to put in. Was I gonna go right to that? Or oh no, one more indefinite one to practice.
Mine's
Do you have a question?
Never mind. No. I was reading something wrong. Sorry.
And Angel, are you doing okay still? Angel, are you still there? I'm afraid.
Angel.
Yeah, my mic's just muted. So
Oh, okay, good.
I have a button. Sorry, I was like trying to find it while I was looking at the screen.
Oh, there you are. Okay. I didn't have my little thumbnails on, so I couldn't see it.
Yeah, I have my cam on. So
As I said, I can see it.
yeah, normally I don't have it on, but decided to have it on today.
Yeah, you do. Good. All right. One more of these. Book exercise 13. Just so we have just a variety of ones to look at. The integral of T, cosecant squared T dt. So this crazy looking one it's not so bad because we could look at, I thought, well, I think TU is going to be T. That was just my first thought. And then I double checked and looked to see in my derivative list and stuff, you know. So the derivative of cotan is negative cosecant squared. So that's great. It's already a packaged derivative. And so now I just need to find the integral of cosecant squared. And they're on the first page of this chapter. And they're also on the back on the integral tables that I'll talk about today. But it's going to be negative cotan. Whoops, I got to call it out though. It's V. V equals negative cotan. So I wouldn't want to do these without having all at least the main values, the main integrals that we know in front of me, like the trig ones and the new stuff that we did with the exponentials and the hyperbolics and those kind of ones. If I have them right in front of me, then I could just scan it and be like, oh, sweet, that's going to work fine. So the integral of cosecant x squared x is negative cotan x. And so then we could just go into the formula. And then the integral of cotan t on the charts is ln absolute value of sine t, which looks awkward for sure. But like I was saying, if we have some number values, which we'll do one next, we have some number values to substitute in, and then we can get an answer that's like a concrete value. That helps make it a little bit more relevant, feel more relevant than this. Do either of you have a question about that one?
No, not on this one. I don't think so.
All right, so this is from the textbook when they start giving you definite integrals. And this helps us practice one last thing. So this is text exercise 27. The definite integral from 1 to 5 of ln r over r squared dr. So this one, not only do we have values to plug in, we also need to think about it like, well, it doesn't look like a multiplication, right? It looks like a division, but actually all multiplications could be written as divisions and vice versa. So like 8 over 5, I could call that 8 times 1/5. So I always could do that and change it into a multiplication. So this is going to be ln r times r to the negative 2. So and you might have seen that already, probably you guys did. But so we could just go, oh, okay, well, I could translate it to my language of the formula now. U du v dv. And I was thinking, well, what would make it, again, like which is going to be the u? I pick I picked the LNR and I like the way it came out, so I think it's okay. And then the DV is the other piece. So V itself is the integral, the antiderivative of r to the -2. So that's going to be negative r to the -1. To me, they're easier on the eye when I just give them the negative exponent like that. So I don't have too many double deckers going on. But you could write it either way. You could write it like -1 over r. That's what V equals also. It's the same as that. So up to you.
Should our R be capitalized too, or does it even matter on the DR?
I know, you're right, Trey. Yeah, it should.
Okay, I just don't know if it made it. Does it technically make it a different variable if one's capitalized and one isn't?
Yeah, it does. So you caught me. Caught me
No,
on that.
no.
Good job.
This is more curious than wanting to correct you.
Excellent. No, I love it when people catch me up on stuff. That's good. On top of it.
Keep your eyes closed, Jane.
So then here I went ahead and combined U and V all at once. So that's U times V. Minus the integral of V times du dr. And so you could see before you even have to do the integral, you could combine these two guys, or girls, ones, these two ones. And this goes to a positive again, like before. Were you going to say something?
Oh no, I just thought it's just guys and girls.
Mhm. So I'll clean this up here and change it to, get rid of those, change that to plus. Change this as 1 over r times 1 over r. Which again, if it's easier to look at it as r to the -2, that's the same thing. Same. However, it's more palatable to you. To me, if I'm doing an integral, I like to look at it looking this way. And we already found the antiderivative of that up here.
Oh, is that why it's plus? Yeah. That was negative before.
Yeah, it's plus because this was minus here. This was already negative.
Oh wait, no, because UV. Okay.
Mhm.
Negative.
Now it's going to go to negative again, actually. So we straighten up all this mess that I'm making. This
Plus
was up to the
du.
-2. So the integral, the whole thing is going to be ln r over r minus 1 over r from 1 to 5. Then finally, you could plug in your values and see if you get 0.478 is about, that's the rounded answer. Whatever variable is going to get simpler when you derive it, do the differentiation, you pick that for you. So
Oh.
in general, what you do. But so like normally, like that one, the last one that I had originally picked, this one I picked t to the 4th first when I was doing this earlier. I picked that to be my u because I was like, well, that'll simplify down a little bit. But then when I did that, that forces this to be the derivative of something, and it's not. It's ln t isn't a derivative of something. It's not on any of the tables or the formulas that we have, and so that's what happened to me. Like I was like, well, crap, what's that then? So then I went back. So sometimes you have to go back and change it, but usually, and that's what they say in the book too, as a rule of thumb, like this one, you pick the simpler one. Oh, come back here. You pick the simpler one.
After you derive it, the simpler one, right? The
Yes,
term with the simplest derivative is.
exactly, right. So like this one's derivative would just be 1. And that's sweet because then in our formula, when we do the du at the end, it just be times 1.
It's just nice and sweet. Okay.
And this one's derivative just go kind of in a circle, you know, would be negative sine 5x times 5. So that would have been worse. Like now we'd have a more bulky thing to deal with. And that happens sometimes. So that's a good question. Yep.
Sweet. Okay, that's kind of, I was getting lost in just using years. So I was like, I better figure this out real quick.
Yeah.
In that, and then this is kind of more of a curiosity thing. Like when the du's or the dx or the dt's at the end, are we actually literally multiplying those against the equation? And that's why it's at the end.
Yeah, in this formula, we are multiplying the du times the what, the v in the formula. Yeah, times the v. We are. But normally, like when we just write it right here, that's just kind of like a formality, like that when you're setting integral, you are always write, like if I was doing the integral of 3x, I
kind of
just
closes it off.
Yeah, and that's saying I'm really taking an anti-differentiation. So I'm saying this is the derivative. I want to go up a step to the anti-derivative. So that's kind of like just claiming like, hey, this is the derivative. So that's why it's sitting there. So that's not times its derivative.
Okay. That's why I was wondering if that's kind of how it worked out, or kind of seems like it's just closing it off a little bit, letting you know when it's ending.
Yeah, I think so. Yeah.
Is antiderivative the same as integral? Are they the same exact thing? Okay.
Yep. The yep.
Definite is just when you have an interval, a given interval. Definite integrals. Okay, sweet. Sorry.
Don't be sorry. That's great. Here's what. Let's just start this one, and then I'll put this one in the assignment because this is one of those 2-level ones. It just gives us one more practice just to set up. Textbook exercise 7 is the integral of x squared plus 2x in parentheses times cosine x dx. So like before, all our other tools from before, we can't use u substitution. We can't like break it apart because it's being multiplied. It's just like a little bit of a beast. But here's our formula again. And so like this one, the derivative of cosine would be negative sine. So that wouldn't be any simpler. So that's the one that's going to be the dv. The u is going to be the little, if there's a simple polynomial like this, that's always the go-to. So like if there's an ln, that should be your u. If there's a polynomial, that should be your u. But otherwise, it's not really a good hard and fast way to be sure.
Okay.
And so then you guys tell me what the other parts would be.
B and cosine x for b. Right? Oh wait.
Did you say? I didn't hear you.
I thought it was cosine x, but yeah, it's dv.
Right. dv is the cosine x. So what's that? The integral of cosine. This is where it's the
Oh, okay. I get wait. Yeah, maybe not.
So this is always
Sine,
the
negative.
integral of what was down below. Yeah. Sine. Good.
Okay. So b is always the integral. Okay.
Yep. V is the integral of dv.
So I think I would have did that one wrong. I would have chose cosine. But
To be your u?
now I get it. It's since there's two terms, it's a given u times dv. The dv is okay.
Yep, it's the u times the dv that's the setup.
The
Good.
world.
Good comments. Nice. And then this derivative is 2x plus 2, just straight down from the u. And I'm not going to keep going through this one, but I'll put this one in the assignment. It's going to be your short assignment, honestly. But we'll just set up this first step. So u times v, whoops. And then if I'm doing these and I'm tired, I might do a little typo with my marker, mess it up. Not when I'm teaching it, hopefully, but
Yeah,
if I'm doing these just to play around with them, I write the number backwards or whatever if I'm tired. So the v was sine x du. So at first it looks like crap. I picked the wrong u. It's still awkward and messy, but not for long. It's just going to need a second level.
Okay.
And so one other thing did you also said that the integral is the same as
Antiderivative. All right.
yes, is the antiderivative. That's a very important conclusion. Yep. And so anyway, then this one, we'd have to go one more. And erase this to make another UV box.
Integral is synonymous.
Yes, synonymous. U and dv. So u would be the polynomial part. dv is sine x. And sometimes, when I first taught this, I'd assign all kinds of ones and then we'd be just doing them in class like for hours. Sometimes we'd go around in a circle and get lost. And the students would get up and do them too. And it was sometimes you could just feel like I'm not assigning the more technical ones, but you can go like 3-4 levels of these to their big old beast. So then v is going to be the integral of your dv. Or the antiderivative of sine of x, negative cos.
Probably bad that every time you say DB, it's really hard for me not to think of domestic violence. I don't know,
To
DB,
think of what?
domestic violence, you know, that's what
Oh
they just call
no,
it a
that's
DB.
true. I think we might have to give it a new name.
I know.
But W wouldn't work either because that'd be like DWI.
Yeah.
I know we have DU and DV. That's terrible. Oh,
Yeah. It's probably.
sorry. Well, we're almost done with it.
No, yeah.
It's triggering. It's not good.
That's true. For someone, it could be. Now that I think about it.
It could be.
Really
Yeah,
could
I'm glad you pointed that out. So I could use different. We could use different letters. We don't have to use those ones. We could even use little smiley faces.
Yeah, right. Great.
Yeah. So anyway, going to this point, if you go this one step further with the red box for this sweet baby right there, it'll finish it off. So that'll get it to the end. So I will assign that one. It's in the web assign. I'll put that one in the assignment. So you guys will have it. You'll be already 2/3 done with it because of this. Do you have any questions about it though?
With the assignment? Or,
About any of this? You're okay, I think. Seems like.
yeah, I think I'm picking this up.
All right. Okie dokes. Let's see. I had page 548 to talk about. This is just a little nod to the integral tables. I might put like 1 or 2 problems on the assignment, not the test though, where you have to use the integral tables. Do you guys, I forget, are you both using the ebook or do you have the hardcover book?
I got the hardcover.
I'm
I
using
use-
the ebook.
Ebook occasionally, but like when I'm
Okay.
in an assignment and it says read it, that's probably the only time I use their ebook.
Yeah. I am that way myself. But
I like a physical book, like old school.
yeah. Okay, well, so if you have in the ebook, Angel, I haven't looked at the reference pages. Does it have those reference pages like I've been referring to?
Back.
So
Can't hear you, bro. Your mic is muted. There you go.
I'm pretty sure, yeah. Just
okay, if
look
you have the
over.
hardcover, they're the blue pages in back.
Oh yeah, okay.
And if you don't, I mean, I could just post a link to all the pages of tables of integrals, but they're reference pages 6 to 10. So it's 6, 7, 8, 9, 10, 5 pages of crazy looking integral formulas. And so that's what we used to use back in the day before, like when I took this, we didn't have technology yet to just have a computer figure out your integral. Yeah. And so we had to only, just like logarithms, we just had pages and pages of tables and we'd have to look them up. And so they still include them in the book, and you'll hear about them in some of the YouTube videos, like Professor Leonard talks about the integral tables. And some people, like real purists, like Ida, I'm sure, would be really hardcore into those integral tables. Whereas I'm more like, use your software or technology when you can. I mean, don't cheat, but if somebody really wants you to use an integral table, you can. But anyway, they talk about that in section 7.6. And so we're just gonna try one, or just one. But I changed to my page. So
reference pages 6 through 10.
So at the beginning they just say, use the indicated entry in the table of integrals to evaluate this integral. So this is just number 1 from our textbook. So 0 to pi over 2 of cosine 5x cosine 2x dx. And then it says use entry 80. Because sometimes you might look at that integral table and I think it's kind of daunting. So if we go back to reference page 5 also has all the derivatives that we could ever want to see. So these reference pages are good, but I'm looking for my reference page entry 80. And like I said, I could post all these on the after class. I'll just see if I can find it in WebAssign, and if it isn't there, I'll just post these in case anyone's just dying to see. So I'm just going to show you what the formula looks like for 80. So this is just the general formula for this particular situation. Cosine AU times cosine BU du equals sine. Oh, and when I was a student, I'd move my finger and totally copy the wrong one and just be like, and then 2 times A minus B.
Just be screwed.
We're not going to do the whole thing even, but I'm just setting it up here.
Holy
Sine
cow.
A plus B. I know.
What?
I don't know if you guys know Ken Franks, but when he took this class, he was like, he discovered these before I taught them. We weren't up to that yet, and he discovered them. He's like, oh my God, look, I could do this one with this table entry. And he'd go up on the board and just loved it. Okay,
Wow.
so anyway.
That's awesome.
It was awesome. He explained them to everybody too, because I hadn't done that much with them, not like this. Anyway, cosine AU, cosine BU, DU equals sine. Yeah. Did you say something?
Oh, I just said, heck yeah. That was cool.
Yeah. So then, all we need to know is, okay, A is going to be 5. And B was 2. And U is X. So we need to make it match up perfectly, exactly to the original. So our formula will fit perfectly. And so then we could substitute those values in. The 5 minus 2 would go here. So that's going to be 3. And 5 minus 2 is here. And sometimes we have to be really careful of the order that they're written in. Every single picky little detail. Every single detail is going to matter in these. So this is A plus B. So people who like doing formulas just really enjoy it. And people who are sloppy and not careful, not so much. Like me, like I sometimes rush, so I'm not careful. I'm not saying you. So just remember the U is going to turn into, X. Hi, Luanda. Luanda's probably like, oh my Lord, what are you doing?
You gotta learn this stuff by Monday for the final. There, have it down.
Good morning.
Good morning. I'm not going to put any integral table problems on the final, but we were just practicing. And then this is going to be, remember, from 0 now coming back down to earth. So we're just using the integral tables here. We did some other stuff first, the one that I'll catch you back up on. And so that should work just fine. Let's see if we can put it right in here. So it's going to be sine 3x over 6 plus sine 7x over 14 minus sine 3 times 0, sine of 0 over 6 plus sine of 7 times 0 over 14. So since it's a definite integral, we could keep going and finish that up. And so remember, we're in radians. If we see pi, then we know that we're in radians.
Oh, that didn't was automatic. Okay, sweet. Yeah. Wait a second.
I just gotta get my calculator and do it too.
In the cosine AU, cosine BU, is it AU and BU in the parentheses behind cosine?
It's the U is, yeah, yes.
Is it
Oh yeah,
that?
look at you writing on there.
Okay, sweet.
So the AU is, yep, is this, that going on.
Awesome.
So sine of 3 pi.
Yeah, have you seen that feature before? It's pretty.
Yeah, I try to usually like I try to get the students to write on there in my beginning algebra classes.
Oh yeah, that'd be cool.
That some of them love it.
People probably get self-conscious about their handwriting and stuff as a beginner.
Right, right, exactly. And then some people don't want to do it. They'll be like, "No, mine doesn't have that."
Yeah.
And I think
Okay.
I can't. Yeah.
Yeah, yeah, what do you do? That's fine.
Sine of 0 is 0, and sine of 0 is 0. So that's just going to be minus 0. Minus 0. So let's see what we got. 0.0137. Anyway, that we could leave it at there. Oh, where was I? I was going to write that final thing, what that equals.
Where did the 3s and 7s come from? Oh, okay.
Oh, the two, back to the formula.
Yeah, okay.
It was A minus B and A plus B. So the first one was A minus B. So A was 5,
Yeah.
B was 2, U was X. So we replaced all of those where they went from the formula. Anyway, so like that, and that's still quite a bit of work, and that's just one of the first problem in that section. So maybe I'll just assign one, just so you guys could practice it. You could, or do more from the book if you ever want to, just to see how it goes. And then I was talking in the very beginning about using computer software like Maple or MathLab or Wolfram Alpha and things like that. If you are going to go on in math, and if you're going somewhere where they'll let you. So like this kind of thing, you could just enter this in. Oh, or the TI calculator will let you, the TI graphic calculators have an integral. They could do the definite integral. And then they have programs too that you could get extra programs, or some of the TIs you could get free apps of them on your computer or phone too. So it's handy. A teacher who really wants you to use the who really wants you to use the formulas in the back of the book and stuff like that, they'll tell you to give exact answers, not decimals. Like I was going into decimals right there, but they'll want you to keep it in exact answers, and that's how they try to keep people from using the computer software and stuff. But honestly, it's all just really advancing and getting better and better, and so it can handle it, like most calculators could even give exact answers, like with radicals and stuff like that now too. So, but I did have one more thing to share before I stop. I have two things. One thing to share on Desmos here, and then and then I'll tell you guys what's going to be on the final, and then I'll post a review sheet, I think. So we were talking one day about how do you get, and some of you might have looked, or not, so there's not that many of you. One of you might have looked into this by now. I don't know, but ooh, I love it. How do we get Desmos to just tell us a derivative? So if I say like f of x equals 8x squared minus 3x, I don't know, there. Well, let's move it up a little bit, plus 2, there. So here's our original function. If we put it in as f of x in Desmos instead of y equals, then we could do a little bit more with it. And I haven't played with this a whole ton. I just was working on it this week since we'd been talking about it. But this will help me, not help me, this will graph my derivative function right there. So the derivative of the f, what?
Oh no, it's got nothing.
Cool,
Sorry.
huh? Yeah,
Yeah,
so the derivative of the f function is that blue one, which you might be like, well, I don't know, what does this really mean? But like what it means, for example, is that say when x, I'm gonna find a good spot. Well, here, where the derivative would be 0 right here at that low point, that minimum point. So when x is about a little bit to the left, when x is about 0.188, then the derivative down here is 0. So that's how you could tell. So if they say like, what's the derivative when x equals 0? What does the derivative equal when x equals 0? And I'd be like, I don't know, like around -1, maybe -1.5. But I could go right over here to my blue function and look at when x equals 0, the derivative is -3. So that's one way. It's like a little bit of a different way than just the TI. I'll just tell you as you trace and enter, you just enter a value on your curve, on your original curve, the red one. You could enter a value and it'll just tell you what the integral is. So it's a little bit different idea, but pretty fun. So I just wanted to show that to everybody. You guys might have more, you might probably know more than me about all these things. But so if you ever do want to share information too, you can. But now I lost come back here. Here it is. The functions too. Remember we were talking about inverse trig functions, and I was looking at some other functions here down. And we have our calculus functions here. Oh, see, we could do d dx also. we could do that of f of x. Once we have it written as f of x, it would do the same thing. So we could use that too. See it just overlaid on top of the blue one because it means the same thing. So if you like Desmos and you've been playing around with it, then you could play with it in this way. Here's our hyperbolic functions. So we could graph those too. Then there's geometry that I haven't even done much with. But I was going to back up here a second to, don't forget we've got this too. So we do have the integral. Let's say, and I haven't played around with the integral. I'm just going to look. The integral from 1 to 2 of that f of x. And I think if I had named it y, it still would have worked.
Yeah, I agree.
Look, it's almost like it heard me say y.
The guy.
Oh, see, now it's not doing it for me. Oh. What if I put it up here? Try. I'm just gonna try one more thing. I know you guys gotta go.
No,
But now see what, once I got rid of f of x, wherever I had referred to it down below, it's gonna have that orange exclamation point because it's like, where's f of x? What is this? You didn't tell us what it was. So
yeah.
but let me go back to that. See if the integral would work here if I just put it on the front. And then went from 1 to 2. I might have to put dx on the back. Let's see if that's what it is. If that still is going to be a problem, then no, there's just dx.
Can you just type it, dx?
Maybe. We'll try. Then I'll stop because this I hadn't tried ahead of time, so I hate to.
That's what I would guess. You just type it.
And then let's put parentheses around here.
Oh,
Yeah.
mhm.
Woo! So
Magic.
look at that. Works. So we don't even need to spend no stinking money on fancy software. We got this. In fact, Desmos hires people. So if anyone wants to work at Desmos, they probably love you. So
Dang.
I know some people who were teachers and went over there to work for them because they create all kinds of lessons and whole curriculum now. In Desmos. Yep. Like teachers use it for their online teaching and everything in class. My son uses it in class too a lot. Students can do like shared activities where they all have a screen and then it projects up to the front onto the smart board and you can see everybody's work, but it's anonymized with different names. It's pretty cool.
That's pretty smart of them.
Yeah, it is smart of them. But yeah, one of my favorite inspirational math guys started working over there like 4 years ago. And then I just saw when I was looking at Desmos the other day, it was like, Desmos is hiring. Are you interested? Not to me. I mean, it was just like a little poster on their site. So, okay, last thing, and then I can talk to you, Luana, about what you missed, or Angel, if you want to talk about what you missed, or do that tomorrow is fine too. Oh, tomorrow's Saturday. No, no school tomorrow. Okay, so the final is going to be covering chapter 6 that we covered, which was 6.2, 6.4, a tiny bit of 6.1. And then the other day when we were doing the hyperbolic ones, we had 6 was this was the trig derivative, inverse trig derivatives. This was the hyperbolic functions, and then L'Hopital's rule. So this is going to be super light. This one, very light. And then today we were doing 7-1. And then 7-6 we talked about, but remember, I'm not gonna put that on the final. So should I put that in like parentheses? It's not gonna be on the final, but we did talk about those integration formula tables. So the final is gonna be about half as long or less, maybe a third as long as the midterm. And the same as how much time it will take. And it'll be on, I'll put it on WebAssign. Because I think I gave you guys enough handouts that you have to do on paper and submit in Moodle. Speaking of which, so double check that you've turned in everything, assignments 1 through 9 before Monday. It's all due Monday night, honestly. Assignments 1 through 9. You all had quiz 1, just one quiz. You did one presentation. You did the midterm. And you'll do the final. So that's where all your grades are going to come from. Okay. If anyone needs me to reopen anything, just let me know. What'd you say, Trey?
I was just gonna say, I wonder if I can do my presentation on Monday before I do the final or something, or
Oh yeah, that would be great.
Okay.
Luana could do that too. Mhm.
is it just like the one we did last semester with Cal? Just do a problem and kind of explain it and stuff.
Uh-huh. Yeah. You can pick the problem, it's fine. At this point, you've seen a lot of things. You could do anything you want of what we've done. That'd be great. Okay, and I'll tell Luana that too. She stepped away. All right then.